So that was my least favorite AP class. Mostly because it was the first year they taught it at my high school and the teacher didn't really know what he was doing. So we just wrote and wrote and wrote and wrote.
That's like that's our first year with the new teacher.
And it's not even AP, it's finals. So
Oh.
do a lot of stuff instead.
Oh, that was the only 3 I got was AP US. Everything else was 4s and 5s. So you'll be in good company if you don't pass that one. Chemistry, calc, stats, Spanish language. And I think that was all that they are. Oh, I didn't take English. So I went to a small school, like even smaller than here, but the AP system was even smaller than it is now 20 years ago. And so we only had about 8 AP classes at my entire high school. So everybody who was you know, an honors student took every AP class pretty much. It was different. Things are different. AP doesn't really transfer that well anyway, right? Did they talk to you guys about that?
Yeah.
Okay. Yeah, it depends. If you get a 3 or above, it'll count as elective credit usually, but not usually for a prereq. So it's, you know, and especially if you're going into that field. So I had to talk with a 5 in the AP chemistry test. I had to talk my way into skipping 1 semester of Gen Chem. They didn't even want to let me do that. So still good elective stuff. Still good practice. I went to a really small school in San Diego called Point Loma. I was one of, I think we had 4 chemistry majors my year. And about, I think we had 12 biochem majors, so pretty small classes. Which is why they let me use that. Yeah. All right, let's start doing some equilibrium. We're basically, there's one major concept that I want to get over today. We're going to review. I guess first I should ask, how did titrations go yesterday? Those make sense now? It's just an excess reactant problem with a 0 excess reactant, right? So a little bit of concentration calculations, you're good to go. All right, so the main thing we're going to talk about today is what do we do when we can't solve for X? When even a solver won't be able to solve for X properly, or if you're in a situation where you don't have access to a solver, like on the test in this class. So we actually do have a way to solve these really complicated quadratics and higher power equations. Kind of. We don't get the real answer. We get close enough for sig figs. So this is actually going to be one case where sig figs are going to help you because they're basically going to make it like a regular algebra problem instead of an x to the 3rd minus 2x squared equals 0, solving that. So let's start by reminding ourselves how we solve for these in general. So let's say we've got a closed system. It initially had hydrogen and iodine as gases, and they go through an equilibrium process where they turn into hydroiodic acid as a gas, so hydrogen iodide gas. If we know the final concentration of the HI, what is equilibrium constant? What is the number for the equilibrium constant? So we can start by writing out the expression for the equilibrium constant. What's the first rule of equilibrium? Products over reactants. So Kc in this case is going to be equal to concentration of HI squared, because the coefficient of 2, divided by concentration of hydrogen times concentration of iodine, both to the first power. So we need to figure out what these are. We know what one of these is, right? This is given in the problem. How do we figure out what the rest of them are? Close, similar. if we have multiple things changing concentration at the same time, initially, we're starting with 0 HI. And we have starting amounts of hydrogen and starting amount of iodine. So if we have everything changing concentrations at the same time, do we have a tool for keeping track of all of those at the same time? Maybe something we just learned on Monday. We have initial amounts. Exactly. Somebody said it. We're going to use an ice table. 1.000 times 10 to the minus 3 moles per liter. 2.000 times 10 to the minus 3 molar. And 0. We have initial amounts of everything. If we have initial amounts of everything, and then everything's going to change, and then we have an equilibrium concentration, we have an end amount. Asen? We have an end amount for HI. Right, so what does ICE stand for in ICE table? Initial change, either end or equilibrium. Turns out you can use ICE tables even in stoichiometry problems. So I like to say end, but the way I initially learned it was the E is for equilibrium. Is that a Denzel Curry shirt? I was just listening to Denzel Curry on my way in today. If you haven't heard it, his cover of Bulls on Parade by Rage is legendary. Not overselling it. Trust me. Anyway, if we know what the end amount is here, 1.87, 10 to the minus 3. That's enough for us to figure out our end amounts of everything. Because we know that all of the change row are all tied together. We can tie them all to the same variable, right? So how much is hydrogen going to change? Not a number. We can say it's going to be gained or lost. It's a reactant, right? So if we're taking reactant to make product, we have to use up some reactant. So we're going to lose some of it. We don't have a number for it yet. So what do we fill in? X. Which means we can do the same thing for iodine, right? Minus. So for every 1 hydrogen and 1 iodine makes 2 HI. So it's going to be the same amount, right? It's also going to be minus X. And then what do we fill in over here? And is it plus or minus? That's enough for us to solve for X right there, right? This column right here, we can say 0 plus 2X equals 1.87 10 to the minus 3. Because all the ICE table is just a way to keep track of a system of equations. Every column is a system of equations, or is an equation. We can say 0 plus 2X equals this amount. Then over here, we're going to have 1.000 e to the minus 3 minus X. And 2.000 e to the minus 3 minus X. As soon as we know what X is, we can know what these are as well. So we can just say 2X, technically 0 plus 2X equals 1.87 10 to the minus 3. Therefore, X is 9.35 10 to the minus 4. Think if I did that right in my head. Then tell me if I got it wrong. Okay. So if we know what X is, we know what all of the equilibrium concentrations are, right? So that's going to give us 6.5, 10 to the minus 4, and 1.65 times 10 to the minus 3. If my math's right. That's all we need to solve for, or to get a number, a numerical value for K, right? We know everything's concentration at equilibrium, so we just do products of reactants. So K equals 1.87, 10 to the minus 3 squared over 6.5, 10 to the minus 4 times 1.65, 10 to the minus 3. Plug all that in. We should get something, we're going to get a total of 10 to the minus 6 on top and pretty close to that on bottom. So K should be in the tens region, I think. Something between 10 and 100. If my math is right. Philip?
Where did you get like the 6.5 and the 1.65?
1 times 10 to the minus 3 minus X.
Oh,
Once we know X, we know all of them, right? I was trying to save space so that these didn't run into each other too much. Remember, capital E is shorthand for times 10 to the. So this is just shorthand for scientific notation. What do we get for a number? Oh, because of the 6 there. Yeah, that makes sense. So it's not as big as I was expecting. I was looking at the exponents. So in terms of doing a reasonableness check, I was looking at the scientific notation exponents. 10 to the minus 3 squared is going to be 10 to the minus 6 on top. And on bottom, it was 10 to the minus 4 times 10 to the minus 3. So we're going to get 10 to the minus 7 on bottom and 10 to the minus 6 on top. So that's going to be somewhere in the realm of 10 for our final answer. I was expecting maybe a little bit above 10, but that's not that far off. If we were doing this, if you're doing your reasonableness check before you hit enter and you were expecting a number to come out like 10 to the 7 and you got 3 as your answer, you probably plugged something in wrong, right? Or your mental arithmetic's wrong. Either way, it's worth thinking about it again. Make sure that you didn't do something dumb on your calculator, right? That's the whole point of our reasonableness check, is that your estimated answer in your head and your calculator answer should come out to be within throwing distance of each other. All right, just one side note real quick. You'll also notice this is specific to at 448 Celsius. Turns out your equilibrium constant changes based on the temperature. When your temperature changes, K changes. So all of the equilibrium constants that you're given are always going to be for a specific temperature. You need more information to try and get the equilibrium constant at a different temperature. But that's the only reason the temperature is included in this problem, is just to be specific. It didn't have to say 448. We never used 448 anywhere in our calculation, right? I could have just written at a certain temperature. All right, let's do another one. Now that I've shown you how to do it, y'all do this one. I'll leave this one up on the board for a minute so you can follow along the example if you need to. You've got an initial concentration of both reactants, and then you have a final concentration of product. What's Kc? The charge. It's just, it doesn't really matter that it's charged for the sake of doing this, that's just telling you what it is. So just treat it like it's any other compound.
Oh, so you need to include it in the fraction.
No, it's not part of the fraction, it's not part of the exponent, right? The exponent is the coefficients turn into the exponents. The reaction balanced. We're good to go there. This is actually kind of an interesting reaction. Thiocyanate, when it makes this complex with iron, it forms a similar type of bond to the sort of bond that holds iron in the hemoglobin in your blood cells. And so it actually is the same color as hemoglobin. So this is actually commonly used on stage for fake blood. Because what you can do is you can put the iron ions in a solution on a rubber knife, and then put the thiocyanate, which is colorless, on the skin of the person who is going to get cut. And then when you draw the rubber knife across the skin, it makes this compound, which is this really deep, like, red wine color. All right, so if we're going to plug this in, we know initial amounts. We'll be able to fill in change with X's. And then we know a final concentration of our iron thiocyanate complex. Basically, we're just going to start by plugging in what we know. If you're not explicitly told how much you start with, you can assume it's a 0. The way that this problem is written says it gives you an initial amount of iron and an initial amount of thiocyanate, and then says nothing about the product. So we're just going to assume the product is 0. Unless you're told otherwise, that's what you should do. Nothing even particularly tricky about the stoichiometry here, right? Everything's just got coefficient of 1. So minus x plus x. So that means this is x, right? So that's going to give 8.3 times 10 to the -4. And 6.3. 10 to the minus 4. Then we just plug it in, products over reactants. So 1.7, 10 to the minus 4 over 8.3, 10 to the minus 4 times 6.3, 10 to the minus 4. Before we hit enter, should our answer be close to 1, less than 1, or greater than 1? Greater than 1. We're going to wind up with 10 to the minus 8 on bottom and 10 to the minus 4 on top. 10 to the minus 4 divided by 10 to the minus 8 should give us something in the ballpark of about 10,000. Plus or minus a factor of 10. What do we actually get when we plug it in? 825. Smaller than we were expecting. We said about 1,000 to 10,000. But we also have if we take into account that's 1.7 divided by 8 divided by 6. That's going to be a couple of factors of 10 off as well. So not that far off, all things considered. All right, so as long as we have initial conditions and at least one equilibrium condition, the ice table is a really handy tool to get all of our final concentrations. Right, and that applies to anything. If we're just doing this with stoichiometry, that would be fine too. If we knew what the limiting reactant was and we were just going to do a stoichiometry problem, if we're actually going to run out of one of our reactants, that just means that one of our end conditions is going to be 0, right? But then you can still do the initial minus x equals 0 and solve for x that way, right? So it's a really useful tool if you've got more than one thing changing concentrations or moles at the same time, because you can keep track of everything simultaneously with one variable. All right, questions on these ones? I forgot that this is the one that we actually are going to use on the next one. Well, we just did 2 of these. I guess this one's a little different because it's in atmospheres rather than molarity. Atmospheres is a pressure unit. What did we say about using pressure units though on Wednesday? They're proportional to molarity, so we can basically do the exact same thing with atmospheres that we would do with molarity. Ice tables work the same way. The only difference is if you have a change in the number of moles, then your K value is going to be different. So you need to pay attention to if you're given KP or expected to calculate KP versus KC. KC, you want everything in molarity. KP, you're going to use pressure units. Other than that, it's literally the same exact process. So 2, SO3. This one's going to look a little bit different when we fill in the change column, because we do have some more interesting stoichiometry here. And we have one reactant making 2 products. So minus 2x, and then our final concentration is 0, or final pressure is 0.48. plus 2x plus x. So we don't know what these numbers are yet, except this is a really easy algebra problem to solve for x, right? Can do this one in our heads. X is 0.01, right? 0.5 minus 0.01 times 2 gives us 0.48. All right. So then what do we get as a value here? The only reason this is worth doing a third time in a row is the different units and the fact that we're going to need to use K on the next slide. So for a known system, we can plug everything in. We're going to get 0.020 squared times 0.010 over 0.48 squared. Big number, small number, or close to 1. I have heard all three possibilities now. If it's close to 1, that means that our top and our bottom are relatively close to the same value, right? Is that what they look like though? Not really. Which one's bigger, top or bottom? By a lot, right? So that's going to tell us if the bottom of a fraction is bigger than the top of a fraction, it's going to be less than 1. By a sizable amount, potentially in this case. Get 4 times 10 to the minus 4, 4 times 10 to the minus 6 over 0.25-ish. So about 1.5 times 10 to the minus 5. So relatively small. You know, we didn't put a number to the coefficient in this case, but the whole less than 1, about 1, or greater than 1 is a pretty good way to do a reasonableness check for these. Just look at your top and bottom of the fraction. All right, why is that necessary? Phil? So your x is always going to come from the column where you know the final amount. We were given this final amount, and we knew the initial amount as well. So if you know the initial amount, you know the change in terms of x, and you know the final amount, you can say 0.500 minus 2x equals 0.48. Right, that's what these columns represent, is your initial, your change, and your end. Your initial plus your change should always equal your final amount. And once you have x for one of these, you know x for all of them. That's the whole point of using the same variable for each of these, and using is that we're really just doing stoichiometry. We're just doing stoichiometry not represented as a conversion factor now. But that's where these minus 2x plus x come from. That is stoichiometry. I wouldn't even call it a different flavor of stoichiometry. It's deconstructed stoichiometry. All right. Any more questions on this one? We're going to use the same reaction. Yeah, Zach. Atmospheres. Again, so don't worry too much about the pressure units at this point. Just know atmospheres is a pressure unit. It represents the average barometric pressure at sea level on Earth. We call that 1 atmosphere because that's the atmosphere we're adapted to. For reference, I think Mars is about 15% of our atmosphere, so 0.15 atmospheres is the atmosphere on Mars. and Venus is like 8 atmospheres. And most of the gas is in the form of sulfuric acid. Venus is a particularly nasty place to live. Don't recommend vacationing there. All right, once we have this value, what if we wanted to use this equilibrium constant to predict equilibrium concentrations? Instead of starting from the equilibrium concentrations to get K, the other place where K is really valuable is that it can allow us to predict what our E column is, or E row. Once we know K, if we know some starting amounts here, like let's say we started with 0.400 atmospheres. And a 0 here and a 0 here. How can we predict our equilibrium concentrations of everything? Or pressures? We can still fill in change, right? Still going to be minus 2x, still going to be plus 2x, still going to be plus x. But now we don't know the equilibrium concentration of anything at the end. It's not the same x anymore because we started from a different amount. So if you wanted to, we could use y, any variable you want. I find it easiest to just stick with x and just know it's different starting conditions. So x is going to be different. So then if we fill this in, we can fill all these in terms of x, and we know what K is, and we know that K is equal to products over reactants, right? First and second rule of equilibrium. So we can write K equals 0.400 minus 2x squared times, sorry, wrong one, products over reactants. I forgot the first rule. 2x squared, x to the first power, 0.400 minus 2x, quantity squared. That doesn't look fun, but that's solvable, right? Not by hand necessarily. Because we are going to wind up with a cubic expression, right? Because we're going to get an x squared here times another x, so we'll have x cubed. Down here, when we FOIL this, we're going to get x squared and an x and a constant value. So we have to do a lot of rearranging just to plug it into the cubic equation, which is no fun at all anyway. This is the point where if you were using a solver, this is a good time to just type it into the solver. If you do that for this class, in most science classes these days, you have to write, I used a solver. I don't want to see this and then x equals unless you tell me how you get to x, because there's more than one way to get there. But it's a valid math step in this class when you're showing your work to say, I used a solver. Set up your equation, plug it in, just make sure you tell me you plugged it in. And most science classes are okay with that these days in college. There will be certain times where you have to solve something by hand once to prove that you can do it, or so that you see a specific trick along the way. But then usually, once you've done that trick, taken the test on that section, most professors are going to be okay with, I used a solver, at least in the sciences.
Final, there going to be anything that doesn't relate, as in,
There is, but I'm going to show you how to do it without a solver on the next slide. It's a math trick. This is what I mean by the sig figs will be on your side in this case. How big was, think back to the first example that we had with this reaction. How big was X? Pretty small, right? X was about 1% of what we started with, 2% of what we started with. If X is going to be really small, 0.400 minus 2x is going to be close to what? pretty close to 0.400, right? So here's I'm not gonna call it a math step because the mathematicians get mad at me when I do that. Here is the simplification step. Is you can write, assume x is close to 0. And we know that even if we hadn't done that previous problem, we can still look at k. K is a really small value, right? If k is a 10 to the minus 5 or smaller, then we can say, we can write this assumption. We're going to need to prove that this assumption is valid down the line. But this will actually simplify this a lot. Because if we assume x is close to 0, we can't just assume x is close to 0 here, because then we'll get 0 equals 1.7 times 10 to the minus 5. That's not going to work, right? But anything where you have a difference, we can assume x is close to 0 and rewrite this. And we can say k is equal to 2x quantity squared x over 0.40 squared. Because x is small, our product concentration is going to be close to what we started with, right? If x is really small, we can say, well, that means that our equilibrium concentration of reactant is about the same as it started. That felt like cheating to me when I first learned it. The math is really tricky. The algebra is a pain in the butt, so we're just going to go around the algebra. But that's what science and engineering does sometimes. There are some math problems that we literally can't solve. Not me personally, like we as a species cannot solve some math problems. So what do you do when those are important math problems? You find a way to make the math easier. You find what assumptions you can make that are going to make the math easier. We do this in astrophysics and aerospace engineering all the time with gravity. We don't have a way. If you have a satellite around Earth, there are 3 significant bodies that all have a gravitational pull on that satellite. You've got the Earth, you've got the moon. What's the third one? The sun. All 3 of those are exerting forces on the satellite at the same time. We don't have a way to calculate the net force of gravity on that satellite. So what we do instead is we say, well, the moon's further away and it's small. The sun's really far away. So we're going to say that the gravitational pull of Earth matters more. We go around the problem. And we just treat it like the only 2 things that exist are Earth and the satellite. And that works. We get good answers that way. As soon as it gets closer to the moon than to Earth, we do the opposite. We assume that the Earth has no pull on the satellite, and the moon's the only thing that matters. So in aerospace engineering, they call that sphere of influence. There's every different gravitational body has its own sphere of influence. When you get close enough to that gravitational body that you're within its sphere of influence, you can ignore the rest of them within sig figs. We're basically doing the same thing here because now we can solve this. Right? We're going to, when we simplify this and fill in our k value, we'll get 1.7, 10 to the minus 5 equals 4x to the third. So 2 squared times x squared times another x. So 4x to the third over 0.4 squared is 0.160. Yeah. We can solve this. This is doable, right? Multiply both sides by 0.16, divide both sides by 4. Going to get something like 2.5 times 10 to the minus 6 equals x to the third ish. Say it louder. Perfect. And then take the cube root. Everybody knows how to do cube root on their calculator by now? If you don't have a cube root button, what do? Put it to the 1/3 power. So. (2.72 10⁻⁶) raised to the 1/3 power. (10⁻⁻2). 3. So to go back to your original question, Diego, about are we going to see one of these on the final when we don't have access to a solver? We're going to have to assume X is 0 if it's a complicated one.
It's more simple to me, just use the root of X or taking that.
If you can solve for it without making that assumption, sure, but it's still going to be a quadratic almost always. And unless you have the quadratic equation memorized, it's not worth it. Even then, probably it's not worth it. It's faster to do this than it is to actually plug it in. If we actually plugged it into a solver the way it was originally written, let's test that assumption. Let me pull up Wolfram. So it was 4 times x to the 3rd over 0.4 minus 2x squared equals 1.7 e to the minus 5. That's not exactly the way I would have written it, but mathematically that's going to come out to be the same thing, right? So here's the exact answer coming out of the cubic equation, which is why we don't want to do that. That's the simplified version. So we get approximate forms. We get 2 that have I in them. We know it's not going to be those solutions, right? 0.0085. We got 0.0088. It's pretty close within sig figs, right? The way we test, again, we won't be able to do that on the test because you don't have access to a solver. So you won't be able to prove your assumptions valid that way. I just wanted to show you that it does give us close to the same answer. The test that we do if you're going to make this assumption, your final step after you solve for X has to be to show that X is in fact small. As long as X is less than 5% of your starting value, then it's a valid assumption. So our starting value was 0.4, right? So is X less than 0.05, 5% times 0.4? .05 times 0.4 is going to be 0.02, right? X is equal to 0.0088. That's less than 0.02. So you just write this, the way you test this, show that you looked at that assumption is you literally write, is X less than 5% of your initial value? And it usually will be. As long as your K value is 10 to the minus 5 or smaller, this assumption will be valid. If K is bigger than that, if this assumption is not valid, we can't use this X value. And we're back to the drawing board, back to go find a solver, basically. So I'm not going to give you one on the closed book part of the test where you can't make this assumption, but you've still got to do the legwork of saying, assume X is close to 0. And then you have to do the legwork of the whole, what is that? 12 characters of writing to say, is X less than 5% of what I started with? And it is, which is a pretty good way to solve for this. If you really wanted to, without using a solver, you can actually get X to be closer to the real value if you do this sequentially. Basically, if you solve for X, making this assumption, and then you plug that X back in here, and then solve for these two X's again, you'll get closer to the real value. You take that value and you plug it in again, you'll get even closer to the real value. Eventually, you'll get the same answer twice within sig figs, and you can say that that's done. That's how solvers like Wolfram handle the fact that once you get to X to the 5th and higher, you can't solve it analytically. It's called an iterative process where you repeat it. You take your first answer and say, well, that's an okay approximation, but I can do better. You feed your okay approximation in, and you do it again and again until you get the same answer twice. I took a whole class on that in grad school, a whole semester long class called numerical methods. Because when you can't solve something analytically means getting the exact answer. When you can't solve it analytically, but you still need an answer, like with our 3-body problem for gravity, you have to use a numerical method. You have to make some approximations. And turns out in engineering, that's kind of a big deal. Knowing when, being able to solve some of these problems that don't have analytical answers or that we don't have the math for. All right. So this is just the rest of the slide on that. So if we can, if K, this says if K is less than 0.01, it's more like if K is less than 10 to the minus 5. It depends a little bit on the exact stoichiometry. That's why we can't just say you can make this assumption as long as K is small enough, because it's going to depend a little bit on the minus X's and the exponents. So that's why we have to write the assumption and then test it every time. All right. Couple more things. So instead of having a quiz this weekend, I want you all to work on the equilibrium and pH assignment from Tuesday, because you didn't have all the pieces to be able to work on that yet. So you should, by the end of today, have all the information that you need to finish that. You'll still have till the next Friday to turn it in, but that's your assignment over the weekend, is to work on that. Right, and this was the big thing that we added today. This is the big tool that we added. Basically, if you see equilibrium, think ice table. And with solving for X on an ice table, if you don't know a final concentration, you either need to use a solver or you've got to make this assumption. Almost always. Right, the last piece that I'll bring up, I already mentioned once, but just to reiterate. So first rule of equilibrium is what? Products over reactants. Second rule of equilibrium is products over reactants. The third rule of equilibrium, solids and liquids don't count. Right, so I'm just reminding you at this point, if you have an expression like this, so lead chloride, lead 2 chloride, on our solubility tables, we would say that that's insoluble in water. Turns out it's not insoluble, it's just an equilibrium process with a really small K value. I want to say that K for this reaction is like 10 to the minus 14. It's a really small amount. So for all intents and purposes, within sig figs, we can say it's insoluble. But really, there's still some amount of lead that's present. Otherwise, we wouldn't really have to worry about lead in our drinking water, right? Because there's chloride in almost everything. So if this was truly insoluble, then lead would never dissolve in water. We know that that's not the case. Small amounts of lead do dissolve in water. Because it turns out everything is an equilibrium problem. And again, I'll go back to grad school. If you go to grad school in engineering or physics or chemistry, you will take, or if you just take the right undergrad pathway, you'll take a whole class on the statistics of equilibrium called statistical thermodynamics or statistical mechanics. It's basically applying statistics to things as small as atoms and the way that they behave. It turns out all of this equilibrium stuff is based on that. So you can explain almost everything in life with thermodynamics, especially if you understand equilibrium, right? So equilibrium doesn't go away. You go anywhere in the sciences. If there's a why question, the answer is almost always because equilibrium. Which is just the simplified version of saying because entropy. Or because the second law of thermodynamics. Talk about a few. We'll have half an hour. All right. This one's conceptual. It's not mathematical. Right, so all you have to do is be able to think about equilibrium. You don't even have to get a calculator out. So this is called Le Chatelier's principle. Le Chatelier's principle just says if you start at equilibrium and you change something, the system will work to undo that change. Basically, because the system needs to get back to equilibrium. So if you're at equilibrium, then you're at the proper ratio of products over reactants, right? At its most basic, that's all equilibrium is. You get to some magical number where you've got the right ratio of products over reactants. If you change anything about that once you get there, if we're at equilibrium and then I add more reactant to the system, what does that do to our ratio? It throws it off. We're not at K anymore, right? If we are at equilibrium and I add extra reactant, the system is going to take that extra reactant and make more product with it. Because it needs to make the bottom of our fraction lower or make the top of our fraction bigger to get back to the proper ratio. Even easier for us by making the bottom side of the reaction smaller, it automatically makes the top half bigger at the same time, right? So basically, if you're at equilibrium and you change anything, equilibrium is going to shift, is the phrase that gets used. The reaction will shift to counterbalance what you just did. Think of it like a teeter-totter. Let's say you had a twin that was exactly your same weight and you got on a teeter-totter. What's going to happen? That's going to bounce, not going to be balanced anymore, right? Let's say I give one twin a big old plate of barbecue ribs and just to hold it. It's no longer going to be balanced, right? That side's going to shift down. If we want it to be balanced again, twin could give half the ribs to the other side, right? Neglecting the weight of the plate. This is not a perfect analogy, but you see what I'm getting at? If you add something to one side, you need to take it from that side and add it to the other side as well. Or if you take something away from one side, let's say both twins have a plate of ribs, and I take the ribs away from one twin. Is it balanced anymore? No, now the twin that still has the ribs needs to give some to the other side. And then it's balanced again. Right, so that whole idea is all this is saying. If a system in equilibrium is disturbed by a change in temperature, pressure, or concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Basically, statistical thermodynamics is saying, stop touching my stuff. Leave my ribs alone. We can watch this. So back to the Haber process. Nitrogen plus hydrogen makes ammonia. This point right here, everything's balanced. You can tell because the concentrations aren't changing. Time is going on, concentrations are staying the same relative to each other. Doesn't matter what they are, matters is that they're at the right ratios. Well, so let's say that at some point we just added more hydrogen gas. That adds more reactant. So to balance that out, the whole thing is going to shift towards the products. In order to get it balanced, we have to shift more of our reactant over to the right-hand side. And the way that I ask questions about this is, I say, here's a reaction. It's at equilibrium. And then I change something. What happens? And the answer is always one of three things. Shift the products, shift to the reactants, or no change. There are some things you can change about a system that don't actually change the equilibrium. Like, example on the last page was calcium carbonate as a solid can react to make calcium oxide as a solid and CO2 as a gas. What is the equilibrium expression going to be for this in concentration units? Products over reactants, right? But what's the third rule of equilibrium? Solids and liquids don't count. So what's the only thing that shows up in the equilibrium expression then? CO2. So let's say the system is at equilibrium. If I add more CO2 to the system, what happens? Slide to the left, slide to the right, no change. I added more product, so it's got to shift to make more reactant. Slide to the left. I can't teach this without getting that song stuck in my head. So now you have to suffer through that too. What happens if I add more calcium carbonate? No change, because it's a solid. Because it's a solid, it doesn't show up in our perfect magic number, right? So adding more solid doesn't necessarily change anything if it's already at equilibrium. If you have 0 calcium carbonate to begin with, you can't get to equilibrium in the first place, right? So all of this is dependent on at equilibrium. If you're not at equilibrium yet, Le Chatelier's principle doesn't work. Once you get to equilibrium, whatever you do, the system tries to undo it to get back to the right K value. The other thing that's really interesting about this is, anybody know what calcium carbonate is? No, that's sodium bicarbonate. Good guess though. Chalk. Calcium carbonate is chalk. Also see it a lot in seashells, eggshells. What this means is that if you just have limestone, there's actually a small amount of CO2 constantly being lost from limestone. Limestone has a vapor pressure. It's evaporating, kind of. It's not really evaporating because you're leaving this behind. But it also means that you can you can take calcium oxide and just dump CO2 into it and make chalk. They've actually proposed this as a way to do what's called carbon sequestration. Sequester something means to keep it separate from everything else. So obviously we as a species have a problem with CO2 in the atmosphere right now, right? This has been proposed as a way to remove some of the CO2 of the atmosphere. You just take CO2 out of the atmosphere and you pump it down to the bottom of the ocean, where we know we have big deposits of calcium oxide. If you do that, then in theory, the high pressure from the ocean water will force the CO2 into the calcium oxide to make limestone, thereby keeping CO2 out of the atmosphere that way. Basically forcing it back into an aquifer instead of letting it be present as a gas. Problem is basically scale. We have way too much CO2 in the atmosphere for that to be much of a viable solution, at least on its own. It might mitigate some amount. It's also going to take a lot of resources to do and energy to do that, right? So at this point, where I believe that proposal ended up is it was going to cause more global warming than it was going to help.
I don't know, in theory, how would they isolate the CO2 to, like, I don't know, if you're pumping the oxygen and they're trying to get just the CO2 in the ocean, how do they isolate it?
There's a couple ways, but one of the ways to do it is basically rely on the difference in size of the gas molecules. Were you here when we talked about reverse osmosis filters the other day? It's possible. So reverse osmosis filters are basically just plastic membranes that have little tiny holes in it that are small enough for water, but too big, or the holes are too small for any ions or bacteria to get through. You could basically do the same thing with gases. You just have a filter that has pores that are small enough for CO2 to get through, but nothing else. Or actually CO2 is larger than nitrogen and oxygen, so you'd probably go the other way. Force the oxygen and nitrogen through the filter, and you're left with mostly CO2 then, or among other things. But basically we separate them by size. The other thing you can do is that CO2 turns into a solid at a reasonably high temperature, relatively high temperature. Anybody know what solid CO2 is? It's come up before in this class. That's solid carbon. Solid CO2 is dry ice. But so dry ice is cold, right? But it's actually a lot warmer than liquid oxygen and liquid nitrogen and the other gases that make up most of the atmosphere. So basically, if you take a big chunk of atmospheric gas and you get it cold, the CO2 will turn into dry ice long before anything else turns into a liquid or a solid, I guess, other than water. You also remove the water by doing that as well. So there's a couple ways that chemists have gotten and engineers have gotten clever with that. Alexander? That's exactly what you do. You get an airtight piston with a vise on the top. So it's not just a piston that moves freely out and in. It's a piston that is on a track that has an inclined plane, just like a vise on a workbench. And you have a spigot on the side of that so that you can fill it up. That's the handle. So you spin this around and you put CO2 in here. When you compress it enough, it literally just turns solid. So you can actually do that. If you have a CO2 tank, you can make your own dry ice as long as you have a setup like this. I used to do it in undergrad for one of our, for my research lab. We needed dry ice, but very rarely. And we had CO2 canisters around all the time because we worked with gases a lot. So when we needed a small amount of dry ice, we just went to go find the vice piston. I don't actually remember what it was called. But vice piston's a good enough name for it.
Like the dry ice, it's like up here, how like.
Basically, yeah. It's not really out of nowhere. The same way that when you have a cold drink, condensation appears on the drink, right? It's not really out of nowhere though, is it? It's from the atmosphere, right? We're basically doing the same thing, except we're doing it by applying a pressure instead of dropping the temperature. If we dropped the temperature, we could do that too. If we had a big commercial grade freezer that got below I want to say dry ice is minus 70 Celsius. We had a freezer that could get a sample of gas below 70 Celsius. We could do it with temperature. Or this is actually a lot easier in most cases. Malik, and then here. Not on Earth. On Mars, yes. Most of Mars is 0.15 atmospheres of gas atmosphere is CO2. So when at the poles of Mars, you can see ice, but it's not water ice, it's CO2. Which typically astronomers are weird. They call anything solid an ice or a metal. So astronomers would say it's CO2 ice. Most chemists that are based here on Earth would call that solid CO2. I've gotten in several debates with astronomers that say that basically anything heavier than anything heavier than helium is a metal. And you basically can only have like gases and ices. They refer to metal ice all the time.
So how people put in ice on Mars, does that, does it like, I don't know, does part of that come in that idea, or is that how accurate?
So there is some amount of water on Mars, but most of the ice that you can see, like if you see a picture of Mars, you can see what looks like polar ice caps, just like Earth, except it's CO2, mostly the little bit of water. Most of the water on Mars is actually under the surface of the planet. Even lower than that in some cases, but yeah, and same with the moon. The moon has some small amounts of water, but it's all way under the surface. Otherwise, it would have evaporated off by now. Yeah.
Be a solution to like refrigerators, like to keep things cold instead of using to use the CO2 that's already in the atmosphere.
If you had a setup like this and you made your own dry ice every day, then yeah. But you need a way to remove CO2 from the atmosphere to purify it. You'd need something like this. It'd be like drawing your own water up from a hand pump well every day. You can do that instead of you tying into the grid. But at what point is it more trouble than it's worth? Refrigeration actually is not that big of a problem in terms of global warming because we can just use electricity. All we need is clean sources of electricity at scale. If we have cheap enough electricity, a lot of these other problems, like even water scarcity, goes away if we have enough electricity because we can just build desalination plants.
How do you get electricity?
Probably fusion. It's probably going to be the biggest thing that makes that happen. Until then, it's still going to be expensive to make electricity. Any other random climate change questions? We've covered everything that I really wanted to cover today. So then here's one last application. This is actually what Fritz Haber did that saved Germany in World War I. Basically, it wasn't just that he figured out how to do the Haber process. He was trying to make ammonia, but the equilibrium doesn't favor making ammonia at very high levels. It's something like a K we calculated was something like 600, which isn't enough to make much ammonia relative to the amount of work it takes to get nitrogen and hydrogen pure and in that system. What Fritz Haber figured out is, well, nitrogen condenses at 78 Kelvin to minus 200 Celsius about. Hydrogen condenses at about minus 270 Celsius. Ammonia condenses at about minus 40 Celsius. So if we just let this reaction reach equilibrium and then get it cold, all the ammonia is going to condense out as a liquid. And then you're going to be left with a bunch more reactant. You basically figured out how to use Le Chatelier's principle and remove product as it was being made. If you constantly remove product, you can't get to equilibrium except by making more product. So he basically found a way to force the reaction to keep going forward past where equilibrium would normally stop it by adding a refrigerator to it. So we had nitrogen and hydrogen coming in here. They had to get up to temperature for the reaction to happen. It needed a catalyst. This wasn't an easy I'm oversimplifying with my explanation. Get your gases, your nitrogen, your hydrogen, push them through a heating coil and through a catalyst. The catalyst is hot, that gets everything to temperature. Then that allows all of these gases to reach equilibrium. And then on this side, through a couple tubes, you had a refrigerator. They got it down below the condensation point of ammonia. So then you wind up with the ammonia dripping out as a liquid. All the gases that are still left at the low temperature, you take those and you feed them back over to the hot side, where they go through the reaction again. But because we removed all the ammonia, they need to make more ammonia to get back to equilibrium again. So it's basically a way to force the reaction to completion, even though equilibrium says that it shouldn't happen that way. So this is kind of the beginning of industrial chemical engineering. All of these concepts were known before Fritz Haber. Fritz Haber was the one who figured out how to put them together and ramp it up to industrial scale. Big enough industrial scale to keep an entire country at war in gunpowder for, I don't know, how long did World War I last? 7 years? Only 4?
World War II?
No, 1. Well, okay, I thought it was longer than that.
1914.
14 to 1919. Oh, 1918, okay. Well, still, 4 years longer than it should have gone. And about 3.5 years longer than it would have gone if not for Fritz Haber. Would have been over in about 6 months. All right. That's all for today. Like I said, work on that equilibrium and pH assignment from earlier this week over the weekends. And don't worry about a quiz. If you don't have anything to do, you can always go up to Reno tonight or tomorrow and go watch the Aces play. If you live in Carson, then you're halfway there.
It's not.